Good afternoon from my side. It's a pleasure to present some of our work, some of our concepts, and discuss them with you. So from all I gathered from this course, this is probably going to be the least technical, most applied presentation. And it's actually structured in two parts. The first is showing some results on how to infer cognitive traits, pathology from brain imaging data using machine learning. And then the second part is going to present some of the ethical, legal, and societal aspects that are extremely relevant when we talk about AI for brain medicine. It doesn't forward. Okay, yeah. So when we look at the human brain using modern imaging techniques such as MRI, EEG, PET, then probably the most striking feature is that there is no such thing as the human brain. Rather, we see a substantial inter-individual variability in virtually any measure of brain organization. And so a key question in neuroscience research, and by extension then also clinical brain medicine, is how do different aspects such as age, gender, genetics, lifestyle, health, how do they contribute to this variability? And probably more important, how does this inter-individual variability in brain structure, function, and connectivity then relates to individual phenotypical aspects, individual behaviors, such as, for example, cognitive performance, or social affective functions, and importantly, when we talk about the clinical aspect, psychopathology. Now, if we look at the field that's been broadly termed biomarker research over the last years, over the last decades, really, the prevailing approach is that of classical within sample significance test, the classical null hypothesis testing. So we do have measures, behavioral measures, MRI measures, and then we compare them between patients and controls. So look at this bar plot here on the lower left. That's a plot I think many of you have seen, most of you probably also have shown at some point or the other. Here we see a highly significant, p less than 0.001, difference in a certain cognitive measure between patients and controls. Is that a good biomarker? Because that's really, if you go through literature, that's how it's always been sold. There's a big difference between patients and controls, so we can use that as a biomarker. Well, I'm going to show you now the very same data, just presented in a slightly more honest fashion, which is actually showing the individual subjects. Now, for those of you that would have considered the left figure to be a viable biomarker, I guess those of you are not so convinced anymore from this plot. And in fact, that's something that is almost universally true. A single feature, any single feature, rarely allows inference on the individual level. In particular, when we're talking about clinical medicine, there's one important but trivial exception here. And these are features that by themselves define the pathology. And a very intuitive example here would be the fasting glucose for the diagnosis of diabetes. So here indeed a single feature, fasting glucose level, does make you diabetic or not. And the reason is that the feature itself is the definition of the disease. So if you have a fasting glucose above 120, then you are diabetic. This is something that is intuitive in the clinical domain, but it really is worthwhile to remember when we're talking about any application of machine learning, of AI to clinical questions. There are quite often, for many different diseases, features that are part of the nosological classification. So you can only have a certain disorder when a particular feature is above or below a certain cutoff. Now, the previous slide has shown you that a single feature is rarely a viable biomarker, but we also have the other point. Now, this is a toy example using basketball players and sumo ringers, and as you see here, their height is statistically not distinguishable. Same for their weight. And moreover, and not unexpected, height and weight are highly correlated. This is exactly the constellation that we see over and over again if we look at biomedical data. You have two groups, there's no real difference in any features, and features are intercorrelated. But the critical thing is that in their combination, through their multivariate pattern, even features that are not statistically different between groups and are intercorrelated can actually yield a good separation between the groups. Now, the big problem here is obviously overfitting. Most trivially, if you have more features than you have subjects, you will always find a decision border, although that will rarely generalize to new subjects. So we really have to change our way of thinking from the classical within sample comparison, where we're basically asking, is the difference in means between two groups surprisingly big, surprisingly relative to our null hypothesis, and embrace what is actually exactly what clinicians ask you. I don't know how many of you have been collaborating or interacting with clinicians. So we are actually running the statistical advisory office at our university hospital. And when clinicians come to me, their questions are always phrased. The initial free-form question, when I just tell them, well, what are you actually wanting to do? They're always phrased as out-of-sample predictions. However, they're usually answered by within sample comparisons, and I hope the last couple of slides have shown you that that's not a viable approach. So rather, we need to train a model based on existing data that learns to differentiate, for example, patients and controls, and then we have to validate it on new samples and see whether the model actually generalizes to new populations. With the advent of big data neuroscience, big data neuroimaging, in particular, the increased availability of large samples comprising imaging data and behavioral data, this has been a burgeoning field. So machine learning of variability and brain behavior relationships in health and disease is something that basically was not a topic 5 years ago, but is a major part of the field nowadays. There are, however, some very important and critical problems. The biggest problem is that brain imaging data intrinsically is extremely high dimensional. So even a single structural scan, which we, or let's say a radiologist, would look at and just scan for a couple of parts, actually consists of 100,000s of individual voxels. And even though I just said that our sample size are growing, they're still absolutely minute relative to the number of features we get from a single scan. And here comes the critical pitch. The key thing is that we do know a lot about brain organization, so we can make our lives a lot easier by actually drawing on prior knowledge on brain organization to reduce the high number of features in a biologically meaningful way. The brain itself is organized along two different principles. One is regional segregation, so different parts of the brain look different and are responsible for different things. And functional integration. So these different modules have to interact with each other to form large-scale networks. First, I'm going to talk a bit about the use of brain cartography or regional segregation. So cortical areas, these modules of the brain, they constrain structure, function, and connectivity, and only have a rather loose relations to macroanatomy. So now what we can do, if we have a large number of subjects that are scanned and processed, we can reduce the, in this case, about 400,000 individual gray matter points. So what you see here on the right side of the black image is regional local brain volumes for 400 individual data points. So we can now use this kind of a priori atlas to basically reduce the number of features from about 400,000 that are highly intercorrelated, because remember, within a particular brain area, things are fairly homogeneous, to a much lower, and through averaging the noise representation, where we only have a few hundred brain areas. So to be precise, we have the regional volumes for a few hundred brain areas, and then obviously the information about the subjects. You can then use machine learning models to train a mapping between this volumetric information and the target feature and evaluate that in new subjects. Here's a first example. And this is, to be honest, the example that is being used most at the moment. Brain age prediction. Can we tell how old somebody is from a simple 10-minute structural MRI scan? Why is that such a popular example? There are two reasons. One is age is something we really have information about for many, many subjects. So we're actually not limited so much by the number of available subjects. And the second, I will develop that a bit, there is that these models actually yield a lot of insight into brain degeneration and pathology. So what you will see here now on the left is a scatter plot for about 6,000 subjects, where on the x-axis we have the chronological age. So how old are the subjects given their passport? And in the y-axis we have the estimated brain age. So how old did the algorithm say that the subjects are based on their structural MRI? And we can see that age can indeed be predicted fairly well from a structural scan. We have a mean average error of about 4 to 5 years, and we can do that fairly well across the whole adult lifespan. Now, does that mean anything, or is it just a nice exercise? Here's a first look. So if we look at healthy controls, HC, then we see that the mean deviation is 0. So some subjects have brains that look older than they are. Some subjects have brains that look younger. And on average, the brain scan looks as old as the subject itself. If we look at patients with mild cognitive impairment, however, so memory problems and a starting loss of function, then we see an increased brain age deviation. So that's positive, and positive means the brain looks older than the subject is by passport. And that effect is even stronger if we look at patients with Alzheimer's disease. Here the brain looks about 10 years older than the subjects really are. In a just published study that was done in collaboration with the Shahid University, we replicated this using a slightly different method and a slightly different sample. And again, we had subjects that were healthy controls in blue. We had subjects with mild cognitive impairment and with Alzheimer's disease. And the focus of the study was then, do we see, well, the focus was twofold. First, can we replicate the previous findings? And second, do we see an effect of sleep-related breathing disorders? Why is that relevant? disordered breathing during sleep, like sleep apnea, is a substantial risk factor for cognitive decline. So we would hypothesize that indeed subjects that are SDB plus, sleep disordered breathing plus, that have these disorders, their brains look older than they really are, indicating a subclinical pathology. And for the health controls, we do not see that. For the patients with mild cognitive impairment, we see again a positive brain age gap. It was not as strong as in the previous study, but still about 4 years. So that they look older than they are. Again, we do not see an influence of sleep disordered breathing. And the same is also true for patients with Alzheimer's disease. Here, we again replicate previous findings, but we do not see an effect of SDB. What's interesting about that is that on one hand, I think that's conceptually important, we use the same method, the same approach, twofold. One is to replicate a previous finding, and then using the same approach, also look at a different factor. And that adds a lot of confidence in that null result in SPD. The other aspect that I think is quite interesting here is that this apparently shows that brain age deviation is sensitive to pathology, sensitive to degeneration, but is not completely unselective, as we see here. Again, subjects with sleep disordered breathing, they are at very high risk for, or at high risk for dementia. It's associated with cognitive decline, but it's not reflected in the brain age gap. And sort of the last study from that series that is based on the same idea is now focusing on Parkinson's disease. Here we had 2 samples, a local one on the bottom, and a top one, we had 2 samples, the PPMI database, a public one, and a local database. So in total, there were about 400 Parkinson's patients and about 200 controls. We used exactly the approach that I just mentioned for data processing and representation. We could compare patients and controls traditionally with each other using univariate statistics, but the more interesting part is here. So how can we address the question that, yes, our models pick up a lot of relevant age-related processes. They pick up a lot of pathology, but they're also rather sensitive to, for example, site-specific effects. So what we used here is a large reference database of several thousand subjects that were coming from many different cohorts. Critically, none of the different cohorts was acquired on the same scanners as either of the 2 clinical samples. And then what we used is a ensemble classification with a stratified subsampling to basically make sure that every weak learner saw something extremely balanced across sites, across age, across gender. Because if you look at the top figure here, you see that there's quite some skew, like the blue data set has many more old subjects than young ones. If we would just train the brain age model here, it would basically associate the signature for the blue site with the signature for old, and we don't want that. So the use of ensemble techniques where every weak learner is completely balanced actually gives us an opportunity to have both a good out-of-sample accuracy and virtually no bias. And that's what we see here. What you see in only very slightly, I have to admit, different colors, is the healthy controls from the 2 samples. And you see the mean average error is less than 4.5 years. And importantly, it has to be remembered again, that this is done on data from new sites relative to the learning samples. If we actually train such model within site, we get a lot better on the accuracy, but it obviously then does not allow us to make any statements about subjects scanned at a different place. If we look at patients with Parkinson's disease, then we see that their estimated brain age is increased. And what we also see is actually that this effect is stronger in the local cohort than in the PPMI. Why is that the case? Well, it's actually quite easy to explain, because the local cohort was comprised of patients that are further along the disease course, whereas the PPMI, a progression initiative, actually recruited mainly very, very early patients. And if we actually look at this quantitatively, so basically, is brain age advancement related to patient characteristics, either the MoCA score, so that's a cognitive feature, so how good is their cognitive performance, or the UPDRS-3 score, how strong are they affected motorically, and we see that indeed brain age advancement is related to both poorer cognitive and motor performance. Now, we could argue that all of that can also be seen by a skilled radiologist. In fact, one of the first things you see in a radiology report is a statement about looks age equivalent, looks pre-aged, looks extremely pre-aged. On the other hand, if you give a radiologist a brain scan and ask, well, is it a man or a woman? They have no chance. However, with these kind of approaches, you can actually classify the gender fairly well. So that's a slightly older data set where we had about 90% accuracy, and we can actually quite easily go up to about 95% accuracy. Now, inferring gender from the brain is not a very useful exercise per se, but it stands to illustrate that we can not only mirror things that a radiologist can do, like age prediction, but we can also actually gain information from images that a radiologist can not get. And finally, and I think this is the direction in which the field is really moving, can we basically tell something about things that are not there yet? Can we make statements about, for example, the further disease course, or in this example here, can we make inferences about whether a particular treatment will be effective or not? And this is obviously where a lot of the field is heading, and this is where I think all of the motivation, all of the buzz, one has to be serious about that, is located. Can we use a combination of imaging techniques and machine learning, AI, to then go beyond what we can do at the moment and actually predict whether a therapy will be successful, predict what's the further clinical course, maybe make statements about adequate treatment or not. And so if you look into the current literature, you find a moderate number of studies that actually use this kind of techniques and approaches. And in particular in the field of psychiatry, you will find an enormous amount of conceptual papers saying that this will be the revolution in clinical brain medicine. Using machine learning on imaging data, we will be able to rewrite nosology, define disorders in a different way. We will be able to have a more precise diagnostic. We will have new information about outcome prediction. We will have new information on potential treatments. And if we put all of that together, I would argue that we are dangerously close to what is referred to as the peak of expected inflated expectations. In fact, this is from the rather well-known Gartner hype cycle, and indeed, most AI applications are fairly much at the peak. So where does it leave us? How do we move on? How do we not only develop interesting techniques, but what is needed, what is necessary, and what is useful when moving into actual clinical application? So that's going to be the second part of my talk. And I can immediately say that I am not providing you with the answers to these questions because they are unknown. But what I hope I will develop is somewhat of an intuition about why it's not so straightforward and why just having a good machine learning algorithm is not yet a revolution in clinical brain medicine. First and most importantly, there are now quite a few studies within brain medicine, but in particular also in other fields of medicine. As you can see here on the left, many of them published in very high-ranked journals that claim that AI is as good, if not better than doctors in detecting a lot of different things. Now that's good, that's encouraging, and that's certainly exciting. The flip side, however, is that these are almost completely retrospective studies. Now, we, and I guess quite a few of you, know that there's a lot of open retrospective data. The ADNI cohort is a good example. UK Biobank is now the big hype. But these are all data sets where you do have all the data available, those features and outcomes, and you can, being deliberately a bit sarcastic here, you can run your models as often as you want until you find something that actually beats clinical diagnosis, and you can publish that. Maybe that's good, maybe that's useful, because we still don't really know yet which kind of models will work well. But in the end, this is nothing more than a proof of concept that it could be doable. And if you look at the charts above, you see that there is a massive discrepancy between the hundreds, I think by now almost thousands of retrospective studies, and the virtual absence of prospective high quality trials. So the picture that we see at the moment is really having a big blank in the middle. We have a lot of published proof of concepts, and then people talk about the revolution of healthcare. But we must not forget that there is a critical step in between, and that is the clinical validation in real world medicine. Another critical aspect then is related to the actual deployment. So let's consider that we do have a randomized controlled trial that can predict the individual response to a certain drug very well. And now imagine maybe not yourself, maybe your parents, no, ideally imagine your grandparents sitting in exactly the situation you see here. Do you think they would be happy to take the drug? It's actually a very good, well-evaluated model. No, they will not be. Now, imagine they go to their family doctor and he or she then says something like this. Well, given what I see, what I hear, and also considering what you're telling me, I would recommend that drug. And if there are problems, we can reconsider. And they will take the drug. We know that they do. What's the big difference here? The difference is related superficially to model explainability, model interpretability. And obviously that's a big field in AI research. And I think we are seeing a lot of advances there. Yet, what is usually considered model explainability is very different from what we would need to actually convince that poor old lady to take the drug, even if it could hurt her. And the critical difference here, is what is termed in philosophy the discursive ability. Discursive ability means that a recipient, like that neat old lady here, has a chance to connect the new information to information she already has. That's something that's termed in philosophy the so-called web of belief. We all have our web of beliefs. We know something about the world. We know something, we know a lot about ourselves. And we have internal models of how all of that is related. And in order to actually appreciate new information, this information needs to be able to get into a discourse to connect to our web of belief. And this is the big difference between the two statements on the right side. The first one, she cannot do anything with. It doesn't connect to anything. The second one actually connects quite well to what she's experiencing and what she's used to. And so from that perspective, one of the most important aspects when we talk about deployment and if we talk about model explainability, explainable AI, is that explainability is not the ability of a model to explain itself to the modeler, but the ability of a model to be appreciated, at least at a certain level, by somebody who has no technical expertise, but only their real life web of beliefs. Now, we all know, and I think that's been covered already in this course, there is this explainability versus accuracy trade-off. Broadly speaking, the better the explainability, usually the lower the accuracy. And that's quite a problem in that respect. Because remember from what I said in the last slide, we don't only need models that are explainable to the modeler, but we need models that are actually explainable to a more or less layperson having their autobiographic web of beliefs. Now, what's our benchmark there actually? Our benchmark has to be current clinical practice. Now let's have a little bit of a look into that, because that shows the big predicament that we will walk into when we start to move towards clinical AI. Assume the following situation. We have a nice model, cross-validated. It's actually not just a proof of concept on retrospective data, it's a prospective trial, and we get 84% accuracy. So if you have a medical condition that's not fatal, that's not massively restricting your life, but it's an annoyance, or it has some potential for long-term harm, like high blood pressure, would you take a drug that does have side effects if you read the model is 84% accurate? So the model says to you, please take the drug, but no, it's only an 84% accuracy. Would you take a drug that maybe has rather substantial side effects that really make your life annoying, like you're sleepy or you're fidgety? You know it's helpful, but they're really, really annoying side effects. And you know it's only 84% accurate. Well, most people would not. But consider our baseline, our benchmark. That young gentleman comes to you and says, I think you would really profit from that therapy. And you would take it. We know people take it. What's the difference? Well, there are two important differences. One is you should not think that this young gentleman has a more than 84% accuracy. It's probably less, and it's definitely unknown. So here, what we have is a very interesting situation that, as I said earlier, interpretability, discursive ability is a key problem. We know that we have a trade-off between accuracy and interpretability. So probably more interpretable models will have a lower accuracy. But then we do have a situation where a model with a known quantified accuracy that may not be close to 100% is competing with somebody that has an unknown accuracy, but a lot of ascribed authority. And what we see is actually that the more precise we can quantify model precision, the more precisely we can say how good a model is, the more precision people will request. For a doctor where we don't know how precise he or she is, we assume precision and believe. For a model where we can exactly say 84% accuracy, we are skeptical because the accuracy is only so low. There we would request 95, 99% accuracy. This seems to a large degree like academic head scratcher and a situation where there's almost a no-win scenario. So because basically medical AI is competing against a system, which is the current medical authority-based system, that probably has a relatively right-shifted explainability accuracy trade-off. But in fact, explainability is unmatched high and accuracy is unknown. So whereas the models always have to deal with this trade-off, the physician does not, because we don't know the low accuracy, we just see the very high explainability. Where does that lead us? It basically means that we need to, at least to some degree, change the way of thinking from many other applications, computer vision, autonomous cars, Industry 4.0, when we move to the medical field. Because if you use AI for optimization in a factory, Industry 4.0, or if you use AI in a medical context, you have one key difference, and that is you need buy-in from the object. And the object in that case would be the individual patient. You can have the perfect AI. If the patient says no, it's useless. So this is something that really needs to be considered and that is yet massively under-considered in the field, that we need to sort of develop our models, develop our validations in a way that is ensuring that we get a sufficient buy-in. And part of that, a big part of that will be that there is something that's probably going to call that's something that's like augmented intelligence. So it's a shared, we will probably see a lot of shared decision-making systems rather than what is currently being hyped as a new autonomous AI-based medical field. And this also, however, has very strong implications on responsibility. And most of you probably know this level of automation that have been developed for self-driving cars from level 0, where there's like no AI, to level 5 that is completely automatic, and there is actually not a steering wheel in the car anymore. And if we transfer that to medicine, then we really have to acknowledge that we will never see level 5 AI in medicine. And we will not see it for two reasons. One is that it's highly unlikely to be accepted. And second is that it creates a massive legal implication on responsibility. So if your doctor treats you wrong, you can sue him or her for malpractice. If the AI gives you a decision that kills you, there's nobody you can sue. There's nobody who can take responsibility. And it's actually something very interesting, and that's why I think that this kind of psychological research related to AI usage needs to be something that deserves a lot of focus. That is something where apparently people make a big difference between health, in the medical field, and all other professions. You are probably quite okay if the AI that is controlling the autofocus of your mobile camera, if that is going wrong, you're probably fairly okay with it, and you're not going to be so okay with AI leaving you permanently disabled. So what I think we will need to see in the future is this shift towards shared decision-making, which is something at the level 2, level 3 of autonomy, where we have an interaction between the healthcare professionals, the physicians, and the algorithms. And that has also important implications for algorithm development, because our goal then should probably not be to just ramp up and squeeze out accuracy, because in the end, it doesn't really matter, but we need to find the optimal trade-off between accuracy, the algorithm should really help, and interpretability. And then automatically we get a shift also in the spotlight, which is not so much accuracy per se, but accuracy in cases where the human physicians try to make errors. That's a field that's not even starting to take off, but I would strongly think that this is where a lot of the research will be heading into the next couple of years. There are two more other aspects that I at least want to mention, and that is, what level of accuracy do we actually want when inferring individual details? You know as good or better as me that we have a lot of ways to quantify absolute error, accuracies, and so on. But if we're honest, then most of these values are, at least at the moment, highly significant, but rather disappointing. Now here comes the catch. For an actual application, we don't need 100% explained variance. And why? That's something you can probably put together from the last couple of slides, because we're not going to have autonomous systems anyways that want to need sort of, or that where the goal would be to be at 100% accuracy, but rather the strong movement there is that we need confidence in our decisions, but rather broad case outputs. So it's more helpful for a clinician if you're asking, how will that Parkinson's disease develop? How bad will the motor symptoms be in 2 years? You can get predicted UPDRS scores with 6 decimal places. Is that going to be helpful to the clinician? No. Is that going to be helpful to the patient? Absolutely no. So rather than looking for very precise answers, we can probably resort to broader categories like good, okay, bad, but we need a high confidence that a patient is assigned to the correct broad category. Last but not least, and that's also, I think, a relevant consideration when we talk about the ethical, legal, and societal aspects of AI and brain medicine. Most of the current medical tests, anything from cognitive testing to bloods to ECG, that is really being done for a specific purpose. You get one value. Now, this is a fundamental difference to data such as DNA, genetics, where it has already been discussed, and brain imaging. Because what you can do, if you have DNA sequencing, what you can do if you have a brain scan, you could potentially ask questions to that data that were not even foreseeable at the time when the subjects actually were measured, when they consented. So a very simple point, you have a brain scan, and that can give you a classifier for whether you have a high risk to develop depression or not. That's useful. That's something that probably your health insurance would be quite interested in. And I think there's a very good reason. They could give you preventive programs, they could monitor you more closely and so on. So let's assume that scenario. Your healthcare provider gives you the opportunity to do a brain scan and then get this kind of test. Now, the problem is that from the same scan, maybe years later, the insurance can also run a classifier to see whether you have a tendency to cheat in your reimbursement claims. This is obviously a constructed example, but what is the critical discussion here is that we have the potential of a proliferation of inferential opportunities, including things in a field as dynamic as neuroimaging and machine learning, including the potential for things that are not foreseeable at the time when you consent towards your data being acquired. To sum that up, what I hope I've sort of shown you over the last roughly hour is that we do now have a lot of potential to objectively assess inner sort of personal traits, both in the field of psychology and in the field of medicine, but we do have a lot of caveats and a lot of implications that come with it. If you're interested in the later, I can really recommend these two articles here where we took a rather high-level conceptual view and discuss some of these issues related to, on the right side, the application in the psychological domain, and the left side in the medical domain. And with that, I am at the end of my talk. I hope I've given you some insight into how we can come from brain knowledge to clinical applications, but also where are the potential caveats and pitfalls. And I would like to thank all of my collaborators, obviously everybody in our institute and the funders. And thank you very much again for the opportunity to speak here and for listening to my presentation. Thanks a lot.
Thank you for joining us today.
Thank you very much for your interesting presentation.
Obviously happy to take questions.
Okay, is there any question? If you have any question, you can write your question in Q&A or raise your hand and I can turn on your microphone. So we have one question. Miss Latifi. You get permission. You got permission.
Hello, hello, Professor. Thank you for your very good presentation. I want, do you have my voice?
Yes, I can hear you very well.
I want to ask you, I wonder that are ML methods preferred compared with deep learning methods in your works or in detecting some disease or not?
Okay, I think it's a highly relevant question. What about deep learning? There's like a 2 or 3 part answer to that. First of all, brain imaging in the past has not really lent itself to deep learning for inter-subject questions. We can do, for example, brain segmentation quite well with deep learning, where you have a lot of data points per subject. But when the objective is to actually learn something about the subject, then our number of samples is the number of subjects. And classically, that is far away from anything that is reasonable for deep learning. Now, I know that people have used deep learning on a few dozen subjects, but that's obviously not going to be useful in the long run. Now, with the increasing advent of larger data sets, in particular, the UK Biobank with about 40,000 subjects, now people are increasingly trying to use deep learning to actually learn this kind of brain behavior relationships. And the effect is, I would say, mixed. There are some cases where it seems that deep learning gives somewhat better results than classical techniques. There are other reports that indicate that, in fact, deep learning may not be better than what you can get with classical imaging. So that's a study we actually published ourselves this year, again on the UK Biobank. And we basically showed that several deep learning methods do not outperform simple kernel regression. So I would say the jury is still out whether with a lot of data, and I really mean like 20, 30, maybe 100,000 subjects, deep learning may be of advantage. It is possible. I wouldn't say that it's impossible. But it seems that in the low to moderate end domain, deep learning is not the answer. And if we then think about clinical questions, we will not have clinical samples of 50 or 100,000 subjects. That's just not going to happen. So in particular, if we look at that domain, I'm fairly confident that we're probably not going to see a big boost by deep learning. And that again also then relates, and sort of the last small part to my answer, to the issue of interpretability and discursive ability, deep learning is, at the moment at least, notoriously bad at that. Is it possible that this will change with new methods? Yes, but we will have to wait for that.
Okay, thank you very much.
Thank you. Is there any question? So, I have some question, Professor.
Yeah.
The first one is about the explainability and interpretability. You have a slide that shows a graph that mentions some methods between their accuracy and their yes, that's it. At first, the more explainability one is a classification. Which classification methods do you mean?
Yeah. So this is a rather classical slide from a 2006 paper. So here, that's usually very simple, like discriminant analysis or something like this. So very low ranked features where you basically try to find a simple classification between two groups.
Something like KNN?
Yeah, I'm not quite sure what they actually meant by that, to be honest, because it's not my slide. But I also know, and this is important to highlight, that there are discussions about where to place different models along that curve, and it's not going to be a linear relationship. So there's, for example, one big discussion I followed a couple of years ago is whether support vector machines are very explainable or very non-explainable. So in that classical paper, they were listed as very non-explainable, and other people have argued they're actually highly explainable. Yes. Another big discussion was on decision trees versus lasso. Here in the Bishop paper, decision trees were seen as rather non-explainable, whereas if you talk to clinicians that are used to flowcharts, they say actually decision trees, that's something that's super explainable to me. And then we come to a very important point. Now, if I have 2 minutes, I want to highlight that a bit. I can't give you an answer to all of that, but I can highlight something. And that is we have to distinguish between model and result explainability. How well can the model explain what it does per se, relative to how well can the model explain why you are being labeled as high risk for relapse. It's a big difference. And the second one is model explainability to the modeler versus model explainability to the subject. And what we will need is a result explainability to the subject. That's actually what your doctor is doing, saying like, you should take this medication because you have this and that. And this is sort of what I cartoonized here. You, not the model per se, I don't give you a lecture about blood pressure and whatever or whatever. You have this symptom. I see this in your examination, and hence you need to take that drug. And you can basically compare. This is classical result explainability to the user. And then model explainability to the expert would be the medical textbook. And if the physician would read a chapter to the poor old lady from a medical textbook, she would not be particularly excited either. And I think this is how you can compare that.
Okay. Thank you. Another question that I have, actually about your answer, you're right, and thank you for your answer. But in my opinion, there are some good. There is some good works in the explainability of some neural networks, such as a capsule network that has been released by Hinton and his co-workers, and it can be improved the explainability of the networks. But as the final question, I have some relevant question about the application of deep learning for a daily life of for improving a daily life a patient with some symptoms. You know, actually at this moment, very different algorithms are used for diagnosing symptoms, and maybe very powerful. There are very powerful algorithms, but there is no algorithm that may have some suggestion and some recommendation, like a recommendation system to improve the quality of daily life of, for example, ASD peoples. How we can do this purpose using deep learning? What's your opinion?
Well, the road there is not so much depending on the learning algorithm, but it's actually something, there's a bit of truth to it. That's something that computer scientists and machine learners cannot do by themselves. What we need...
They need data. They need
right,
data.
they need particular forms of data. They need longitudinal and or interventional data. So basically, if you want to improve, if you want to know whether you should recommend drug A or drug B to a patient, you cannot do that based on just having a lot of data from patients. Rather, what you need is a lot of data from patients that were then randomized into the two groups and then had their outcome monitored. So here you have both the interventional aspect, you give drug A or B, and the longitudinal aspect, you monitor the outcome. And this is data that at the moment is still somewhere between super rare and non-existent. There's a lot of talk of using hospital databases for the retrospective analysis of such things. And I've actually had some longer discussions with some computer scientists that were very enthusiastic about this idea. Well, let's just go back and mine a hospital database, see whether we can predict good outcome to drug A or drug B. There you have one confound that is actually invisible to the modelers, and that is that in real life, whether you get drug A or drug B, that both are reasonable choices, is not a random decision, but it's actually something that is an interaction between the presentation of the patient and the prescribing physician. And so this is what makes any sort of retrospective analysis of these aspects somewhere between very tricky and probably, I wouldn't say impossible, but not very useful. That's why we need the interaction between the users and the modelers.
Thank you very much for your interesting and your complete answer, and thank you for joining us. And is there any questions?
Doesn't seem so.
Okay, thank you.
So we again thank you, Doctor. With this, we finish this part of our symposium, and
enjoy the rest of the whole course. Thanks.
Thank you very much.